Welcome to Behind the Scenes of Iconic Buildings, where we explore the hidden engineering brilliance that transforms architectural dreams into reality. Today, we'll dive into the structures of some of the world's most iconic buildings, revealing how they stand tall against gravity, weather, and time. 1. The Burj Khalifa. Let's begin with the Burj Khalifa in Dubai, the tallest building in the world. At 828 meters, it's an engineering marvel. But what makes it stand? Its Y-shaped design isn't just for aesthetics, it provides stability. The building uses a buttressed core structure. Essentially, three wings extend outward from a central core, each reinforcing the other, resisting the high wind forces at such extreme heights. Additionally, the building's tapering shape reduces wind load as it climbs higher, ensuring it sways safely rather than dangerously. 2. The Sydney Opera House. Now, let's head down under to the Sydney Opera House. Its stunning sail-like shells are a feat of structural engineering. These aren't simply curved panels. They're a series of precast concrete ribs. The engineers created a solution where each shell is a segment of a sphere. By using spherical geometry, the design simplified both construction and load distribution. It's the perfect marriage of form and function, blending art with practical engineering. 3. The Eiffel Tower. We can't talk about iconic structures without mentioning the Eiffel Tower. When it was built in 1889, many doubted the safety of such a massive iron structure. But Eiffel's team used a deep understanding of structural dynamics. The iron lattice reduces wind resistance while maintaining strength. Its unique design allows for slight movement during strong winds, distributing stress across the tower. That flexibility has kept it standing for over a century, proving that even metal structures can bend without breaking. These masterpieces of engineering are more than just beautiful, they're feats of innovation. From wind-resistant skyscrapers to geometrically inspired shells, these buildings embody the perfect balance between art and science. And next time you gaze upon one of these structures, you'll know just a little more about the brilliance holding them up. Thank you for joining us on this behind-the-scenes journey. Subscribe for more insights into the world of engineering and architecture. Welcome back to Blueprint to Reality. Today, we're exploring one of the most critical forces in structural engineering, shear force. Whether you're building a simple house or a towering bridge, understanding shear force is essential for ensuring the stability of any structure. But what exactly is it, and why is it so important? Let's break it down. What is shear force? In simple terms, shear force refers to the internal force that acts along a structure's surface, causing two adjacent parts of the material to slide past each other. Imagine holding a deck of cards and pushing the top half sideways. The cards move relative to each other. That's the same idea as shear force in a structure. When external loads like wind, weight, or even earthquakes push on a building, shear forces occur inside the materials. How does shear force occur? Shear force is a direct result of loads acting on a structure. For example, when a beam is subjected to loads from above, part of the beam tries to move vertically, while the other part resists this movement. This creates shear forces within the beam, which can lead to cracks or even structural failure if not properly accounted for. Shear force diagrams help engineers visualize how these forces act along the length of a beam or structure. The higher the force in a particular area, the greater the risk of structural damage if not designed carefully. Why does shear force matter? Shear force matters because it directly affects a structure's ability to resist failure. If shear forces become too great for the materials to handle, the structure may experience 1. Shear cracking. This happens when materials break along a plane where the shear force exceeds the strength of the material. 2. Buckling. Shear forces can also cause structural elements like beams and columns to buckle or bend, leading to potential collapse. 3. Structural instability. Even small shear forces, if left unchecked, can weaken a structure over time, making it unsafe for continued use. To combat these risks, engineers use reinforcements like steel bars in concrete or diagonal bracing in tall buildings, designed specifically to resist shear forces. Shear force in everyday structures. You encounter shear forces every day, often without realizing it. Take a simple bridge, for example. As vehicles move across, the bridge experiences shear forces along its supports. In skyscrapers, wind creates lateral forces that introduce shear into the beams and columns. Engineers carefully calculate and design around these forces to ensure the structure can safely resist them. So, why does shear force matter? Because it's a silent but powerful force that can dictate whether a structure remains stable or fails catastrophically. Thanks for joining us today on Blueprint to Reality. Be sure to subscribe for more insights into the fascinating world of structural engineering.
See you next time.
Welcome to Blueprint to Reality. Today, we're diving into a topic that's both fascinating and crucial for civil engineers: why bridges fail. From ancient times to the modern era, bridges have connected people, economies, and cultures. But when a bridge collapses, it's a powerful reminder that even the best designs can fail under certain conditions. So, what causes these failures and what can we learn from them? Let's explore. Design flaws. One of the most common reasons for bridge failure is design flaws. Engineering is all about precision, and a small miscalculation in the design phase can lead to catastrophic results. Take the infamous Tacoma Narrows Bridge, which collapsed in 1940. Designers underestimated the effects of wind-induced vibrations, causing the bridge to twist uncontrollably and eventually fail. Modern design codes now account for aerodynamic forces, thanks to this lesson. Material failure. Materials can also be the culprit. Bridges are subjected to constant stress from vehicles, environmental conditions, and natural wear over time. In the case of the Silver Bridge collapse in 1967, a single steel I-bar cracked due to corrosion and material fatigue. This small failure triggered the collapse of the entire structure. It highlighted the importance of regular inspections and the need for materials that can withstand long-term stress. Poor maintenance. Even a perfectly designed bridge can fail if it's not maintained properly. The Morandi Bridge in Italy collapsed in 2018, killing 43 people. While the design was innovative for its time, the collapse was linked to poor maintenance and corrosion of key structural elements. Regular maintenance and inspections are essential to ensure the safety of bridges, but budget cuts and neglect can lead to deadly consequences. Environmental forces. Bridges must also endure environmental forces such as floods, earthquakes, and extreme weather. The Minnesota I-35W bridge collapse in 2007, which killed 13 people, was partly due to an inadequate design to handle the loads it eventually carried. Additionally, climate change poses new challenges as rising temperatures, more frequent storms, and increased flooding are putting extra pressure on aging infrastructure. Bridge failures are often a combination of multiple factors, whether it's design flaws, material issues, lack of maintenance, or environmental forces. But from these tragedies, we learn valuable lessons that help engineers design safer, more resilient structures. If we continue to push the boundaries of innovation while learning from past mistakes, we can build a future where bridges not only connect places, but protect the lives of the people who cross them. Thanks for tuning in to Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more insights into civil engineering and structural design.
See you next time.